Right, we're now going to have a look at the reaction of alkenes with hydrogen halides. So just to recap, hydrogen halides could be hydrogen chloride, hydrogen bromide, or hydrogen iodide. Okay. And in terms of their reaction, so again, it's going to be an addition reaction. So let's firstly do the overall reaction. So again, just with ethene, like so. So let's do HBr, let's do hydrogen bromide. And again, we're going to form one product, a saturated product. And we're going to add hydrogen to one carbon and bromine to the other. So that would be our product over here. Okay, so overall it's an addition reaction. We now need to know what the reaction mechanism is. So like we did with halogenation, for hydrogen halides, we do also need to know what the reaction mechanism is. So in terms of drawing out, we've got our ethene drawn out. Our HBr, just remember, so any hydrogen halide, so that's just any halogen, so it could be chlorine, bromine or iodine. Remember, the halogens are more electronegative than hydrogen, so that means the electrons in this bond are always going to be closer towards the halogen than they are to the hydrogen. So that means all of these are going to have a permanent dipole. So with halogenation, with halogens, it's an induced dipole. It's only when that halogen molecule gets close to the double bond does it have an induced dipole, whereas these ones here will always have a permanent dipole because of the difference in electronegativity between hydrogen and halogens. So our HBr, we need to draw it so the hydrogen delta positive is closer towards the double bond and the bromine delta negative is further away. Okay, this again is an area of, electron richness, so it's got a lot of electrons there. Here our HBr is our electrophile because it's going to accept a pair of electrons at the hydrogen delta positive end. Okay, so this is electron rich, this is electron deficient, so that means our curly arrow must start, as usual, from the double bond going to our hydrogen delta positive. Over here, hydrogen can't have more than one bond, so that means this bond here must break. So curly arrow from that bond to the Br delta negative. Remember, this type of bond breaking, so this where the bond's breaking here, is heterolytic. So it's heterolytic fission. That's worth remembering because you could get asked that in the exam. So next step is, so that pi bond is broken. Okay, we formed a bond. So I'll draw the other hydrogens in first. We formed a bond between the carbon and the hydrogen. Okay, and this carbon here has a positive charge, so it's our carbocation. And we also have, because remember the electrons here, the bromine ran off with the electrons there, so it's bromine with a negative charge and a lone pair. We then draw our curly arrow from the bromine lone pair to the carbon the carbon positive, and that then forms our final product, which is this. Okay, so that's the reaction mechanism for the reaction of alkenes with hydrogen halides. Now, one thing that's worth noting is that with ethene it doesn't matter because ethene is what we call a symmetrical alkene. But when we have an alkene that's not symmetrical, it matters which way around the H and the Br or the H and the halogen attach. So let's now do an example of that, because in an exam you could be asked to predict which product is the major product, so which one is going to be formed at a greater percentage. So let's pick our propene. Okay, so again, I'm going to draw my hydrogen bromide. Let's just do it with hydrogen bromide again. So it's got a permanent dipole going across that, and curly arrow from the double bond to hydrogen delta positive, and then the HBr bond breaking like that. Okay, and now you have two choices of what can happen. So one could be that the hydrogen attaches to the middle carbon, like that, and you form your carbocation here and your Br delta minus here. Okay, not Br delta minus, Br minus. Or the other product you could get is this one here. Where the hydrogen attaches to that carbon and your carbocation is here. And again, Br negative there. Okay, so what we've now got to do is think about which of these, remember these are intermediates, so they're not the final product yet, which intermediate is more likely to occur. Okay, and from there we then have to predict which one is the major product. So hopefully you can see that once this reaction finishes here, so once we do the final curly arrow, the Br will be attached here, so that's one product. And when I finish this one here, the Br will be attached to the middle carbon, so that's the other product. So we've got to decide out of these two products, which one is our major product and which one's our minor product. So major is the one with the higher percentage in terms of, you know, yield being produced, and the minor one is the one that's going to be produced is in the smallest percentage. Okay, so what we've now got to do is look at the carbocations. Okay, these intermediates here will tell us which one is more likely to form. Okay, so with this one, the carbocation is on this carbon, and this one here, the carbocation is on the middle carbon. Okay, so what we now need to do is to name these types of carbocations. So when you have a carbocation that is attached to one other carbon, so this could be anything coming off here. Okay, so when you have a carbocation where the carbon with the positive charge is bonded to one other carbon, okay, we call this a primary carbocation. Okay, I'm just going to rub out this first part because I need some space. So I'll leave both of these here. When we have a carbocation where the carbon is bonded to two other carbons and only one hydrogen, like so, this is called a secondary carbocation. And obviously where you then have, I'll draw it here, a carbocation where the carbon is bonded, the carbon where the positive charge is bonded to three other carbons, this is called a tertiary carbocation. Okay, out of these three different types of carbocations, a tertiary is more stable. A primary is the least stable. If tertiary is more stable, that means it is more likely to form and therefore lead to the major product. A primary carbocation is less likely to form and therefore will usually lead to the minor product. So let's now have a look at these and let's classify these different types of carbocations. This one here, if we look at the carbon with a positive charge, this carbon is bonded to two hydrogens, only one carbon. So this one here is a primary carbocation. And this one here, so this carbon here, is bonded to two other carbons. So this is called a secondary carbocation. Okay, secondary is more stable than primary, and therefore this carbocation is more likely to form than this one. And that means this one is going to lead to more product. If this one's more likely to form, this one is the one that's more likely to form the product. And that means in terms of your final product, I'm just going to draw it over here. So this one is going to lead to this product. and this one's going to lead to this product. Like so. So as we said, because this one is formed from the secondary carbocation, secondary is more stable than primary. This one here, where the bromine's attached to that middle carbon, this is what we call the major product, or the one that's produced in the greater percentages. And this one here will still form, okay, but it'll be a very small percentage. So this is called our minor product. So we have our major and minor product. And the way that you decide that is by drawing out the mechanism for both, so the formation of both of these carbocations and both of these products. And then from there, you classify the carbocations and then decide which one is more stable. And therefore, the more stable one will lead to the major product. Okay. There is another way of doing it. So it's called Markovnikov's rule. So I'm just going to draw that out. In an exam, however, I personally wouldn't refer to Markovnikov's rule. I would refer to the stability of the carbocation, but I will cover Markovnikov's rule as well. Okay, so Markovnikov came up with a rule to help you decide out of these two which product is more likely to form. So the rule goes like this. So the hydrogen in the hydrogen halide will attach to the carbon with the most hydrogens on it. Okay, so in terms of our propene, I'll draw that out again. Okay, so that was our starting reactant. Out of these two carbons, so according to Markovnikov's rule, the hydrogen in the hydrogen halide, HBr, that is going to attach to the carbon with the most hydrogen. So this carbon here has only one hydrogen, this carbon here has two hydrogens, and therefore the H in HBr will attach to this carbon. And therefore when you form your product, it will be there and the Br will be there. And this is the same as this major product that we've drawn there. But as I said, sorry, I'll draw it like that. As I said, don't use that in an exam when answering your question. Use the stability of the carbocations to answer your question.